Tonight, we're going to look at where we actually live in this galaxy. The full, three-dimensional structure that contains us on a galactic scale. It's called the Orion Arm. Every star you've ever seen with the naked eye is inside it. Every planet we've ever visited, every probe we've ever launched, every telescope image we've ever taken of something we called close, all of it comes from the same structure. Most people know we live in the Milky Way, but almost nobody thinks about what part of it we're in, or the true scale of it. By the end of tonight, you're going to see just how vast this structure really is, and just how small we are inside it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Milky Way is a barred spiral galaxy. That's the formal classification, and it means something precise. At the center sits a dense, elongated bar of stars, stretching roughly 27,000 light-years from end to end. From the ends of that bar, spiral arms unwind outward, like water spinning off a wheel. These arms are not solid structures. They're not walls or tubes of material floating in space. They're regions of higher density, zones where stars, gas, and dust are more tightly packed than in the gaps between them. Think of it less like the arms of a starfish and more like the bands in a whirlpool, regions where material slows down and piles up as it moves through. The Milky Way has 4 major arms. They're named Perseus, Norma, Scutum Centaurus, and Carina Sagittarius. Each one is a primary structural feature of the galaxy, stretching for tens of thousands of light-years, containing billions of stars, and reaching from near the galactic center out toward the outer edge of the disk. And then there are the minor arms, smaller spurs and bridges that branch off from the major ones. We live in one of those. The Orion Arm, sometimes called the Orion Spur, or the local arm, is a partial arm of the Milky Way. It branches off from the inner edge of the Perseus Arm and extends outward at a slight angle, threading through a region roughly halfway between the galactic center and the outer rim. We sit inside it. Our entire solar system, every planet, every moon, every asteroid and comet and spacecraft we've ever launched, all of it is embedded in this spiral feature, roughly 26,000 light-years from the galactic center. For most of the 20th century, astronomers classified the Orion Arm as genuinely minor, a small spur, a modest connecting bridge between 2 larger arms, not a real arm in its own right. That picture has changed dramatically in the last decade. New data from missions like Gaia, the European Space Agency's Space Observatory, that has been mapping the positions and motions of stars across the Milky Way with extraordinary precision, has revealed that the Orion Arm is far larger, far longer, and far more structured than anyone previously thought. We're not living in a cosmic backwater. The revised picture puts the Orion Arm at somewhere between 10,000 and 25,000 light-years in length, possibly longer. Its width spans several thousand light-years. It contains an enormous number of young stars, active star-forming regions, and massive molecular clouds where new stars are still being born right now. It is a substantial structure in its own right, just not classified as one of the 4 main arms because it doesn't extend from the galactic bar outward in the way they do. The name itself tells you where we got our first clue about it. The constellation Orion. When you go outside on a clear winter night in the northern hemisphere and look toward Orion, you're looking in the direction of some of the Orion Arm's most dramatic features. That distinctive pattern of stars, the three-star belt, the bright blue-white supergiant Rigel at one corner, the red supergiant Betelgeuse at the other. The fuzzy smudge just below the belt that you might mistake for a dim star at first glance. All of it is embedded in or directly associated with the Orion Arm. That fuzzy smudge is the Orion Nebula. It sits roughly 1,340 light-years from Earth, close in galactic terms. The Orion Nebula is one of the most active star-forming regions in our galactic neighborhood, a churning cloud of gas and dust, roughly 24 light-years across, where gravity is currently pulling material together into new stars. Some of those stars are already forming. Some already have protoplanetary disks, rings of gas and dust swirling around newborn stars where planets may be assembling at this moment. When astronomers point the James Webb Space Telescope at the Orion Nebula, they see something that takes a moment to fully absorb. They see the process of solar system formation happening in near real time. The light we're receiving left the nebula around 13 centuries ago, but the physics hasn't changed. New suns are switching on in that cloud right now. The Orion Nebula is not a relic. It's a factory, and it's one of the reasons the Orion Arm gets its name. It's the defining landmark of the arm, as seen from Earth, the most dramatically visible feature of the local galactic structure when you look up at night. But the Orion Nebula is just one feature. The arm stretches in both directions from our position, filling a region of space that contains thousands of stellar nurseries, tens of thousands of young massive stars, and more raw material yet to be processed into new suns than exists in most parts of the galaxy outside the primary arms. To understand the true scale of the Orion Arm, you have to start with the unit astronomers use for these distances: light years. 1 light year is the distance light travels in a single year at its full speed of about 186,000 miles per second. That works out to roughly 5.9 trillion miles. The Orion Arm, at its revised estimated length of somewhere around 25,000 light-years, is therefore on the order of 150 quadrillion miles long. That number is effectively meaningless when spoken out loud. No human brain evolved to process scales like that, and it would be dishonest to pretend that simply hearing it creates any real understanding. So, instead, think about it in terms of time. The fastest spacecraft currently traveling away from Earth is Voyager 1, moving at roughly 38,000 miles per hour. At that speed, to cross the Orion Arm from one end to the other would take roughly 450 million years. That's 450 million years of continuous travel at the speed of the fastest spacecraft currently leaving our solar system. And the Orion Arm, let me be clear, is not a major arm of the Milky Way. The Perseus Arm, one of the two dominant arms, stretches roughly 65,000 light-years. The full diameter of the Milky Way's disk is somewhere around 100,000 light-years across, with some estimates pushing further. The Orion Arm is a feature inside that system, and crossing it at Voyager's speed would take the entirety of the Cambrian explosion to the present day, with time to spare. That is the scale of where we live. Not the scale of the universe. Not the scale of the observable cosmos, which stretches about 93 billion light-years across. Just the scale of the arm we live in. Just our local portion of one galaxy. Now let's look at what actually fills that space. Because the scale only becomes real when you understand what's in it. Stars, primarily. The Orion Arm contains billions of stars. They range from massive blue giants burning through their fuel in just a few million years to dim red dwarfs that will keep quietly fusing hydrogen for hundreds of billions of years, long after the Sun has expanded and cooled and gone dark. The Sun itself is an average star, not particularly large or small, not particularly young or old. It sits about 4.6 billion years into its estimated 10 billion-year main sequence lifespan, classified as a G-type main sequence star, sometimes called a yellow dwarf, though from space it would appear white rather than yellow. Its luminosity is 1 by definition. Every other star gets measured against it. When you look at a star and see it's 10 times more luminous than the Sun, that means it's releasing 10 times as much energy per second into the surrounding space. In the Orion Arm, you can find stars millions of times more luminous than the Sun. Stars like Eta Carinae, which sits roughly 7,500 light-years away in the Carina region at the far end of the arm. Eta Carinae is a stellar monster. It contains somewhere between 100 and 150 times the mass of the Sun crammed into a single gravitationally bound object. It's burning through its fuel at such an extreme rate that it's expected to end its life in a hypernova, a kind of explosion far more energetic than a standard supernova, at some point in the next few 100,000 years. When it does, the burst of radiation it releases will be detectable from Earth, even at a distance of 7,500 light-years. Not dangerous to us, but measurable. Eta Carinae already had a major outburst in the 1840s that briefly made it the second brightest star in the night sky, visible in daylight, without actually triggering a supernova. That was a near miss on a catastrophic scale. It shed mass equivalent to several times the mass of our Sun in the span of a few years. The material it ejected is still visible today as the Homunculus Nebula, a dumbbell-shaped cloud of gas and dust surrounding the star, expanding outward at about 400 miles per second. And Eta Carinae is still there, still unstable, still building toward an ending that will be one of the most violent events in the local galaxy when it finally arrives. The Orion Arm contains dozens of objects in states of dramatic instability, massive stars in the final phases of their lives, burning too hot and too bright to survive long by cosmic standards. And thousands more that haven't quite reached that stage yet, blue and blue-white supergiants, still in what passes for the prime of their short, intense lives, pouring out ultraviolet radiation that would be lethal to any unprotected biology within a few light years of them. This is the neighborhood, not a gentle, stable zone of quiet suns. A region filled with stellar extremes, from the smallest dim red dwarfs you'd need a telescope to detect to the largest and most violent stars in the local galaxy. Both extremes coexist in the same arm, at different distances, in very different parts of its length, but part of the same structure. One of the most important recent revelations about the Orion Arm is the recognition of how much internal structure it actually has. It's not a uniform band of material. It contains distinct concentrations of star formation grouped into recognizable regions, connected by filaments of gas and dust, separated by zones of relative emptiness. Astronomers have mapped several major star-forming complexes within the arm. The Orion Molecular Cloud Complex, the closest large star-forming region to our solar system, spans hundreds of light-years and contains the Orion Nebula as just one component of a much larger system. Within this complex, there are multiple distinct clouds at different distances and in different stages of evolution. The Orion A cloud contains the Orion Nebula and the dense stellar nursery behind it. The Orion B cloud, slightly further away, contains a different collection of young stars and protostars. Further out in the arm, there's the Ophiuchus star-forming region, roughly 450 light-years from Earth, where protostars are still collapsing from clouds of molecular hydrogen. The Ophiuchus complex is a darker, quieter kind of star formation than Orion. It's mostly making lower-mass stars rather than massive blue giants. But it's still actively manufacturing new suns from raw material, right now, at a distance of 450 light-years from where you're sitting. The Perseus molecular cloud sits roughly 1,000 light-years out, a dense concentration of gas where dozens of young stellar objects are currently in various stages of formation, some just beginning to condense, some already hot enough to be visible in infrared, some surrounded by disks that may form planets within the next million years. The Taurus molecular cloud, roughly 450 light-years distant, is one of the nearest active star-forming regions to the solar system. It's quieter than Orion, forming lower-mass stars, but it's still producing new suns from the same basic ingredients: hydrogen gas, dust grains, and gravity. All of these regions are features of the Orion Arm. All of them are active, ongoing, dynamic. And all of them are visible, at least to our instruments, from the surface of a small rocky planet sitting quietly inside the arm that contains them. The Milky Way takes about 225 million years to complete one full rotation, one orbit of the galactic center. That period of time is called a galactic year, or sometimes a cosmic year. Our solar system has orbited the galactic center roughly 20 times since it formed. In one galactic year, the entire configuration of the spiral arms changes substantially. Stars that are currently inside the Orion Arm won't be in it the same way a galactic year from now. This is because spiral arms are not made of fixed stars moving as a group. They're more like a traffic jam. Picture a busy highway where cars slow down near an obstacle. The jam appears to have a fixed location, even though the individual cars are always moving through it. New cars arrive from behind, slow down, pass through, and continue on the other side. The jam persists, even though it's never made of the same cars. Spiral arms work similarly. They're density waves, regions where gravity causes material to pile up and slow down as it passes through, making those regions appear brighter and more active, even as the individual stars inside them constantly drift in and out. The Sun is currently passing through the Orion Arm at a relative velocity of a few miles per second compared to the arm's average motion. It has spent time in the arm. It will eventually drift out of it, and over billions of years, it will pass through multiple spiral arms as it continues orbiting the galactic center. The encounter between a solar system and a spiral arm has physical consequences. When the Sun passes through denser regions, it encounters more material, more stellar neighbors, and potentially more disruptions to the distant cloud of comets that surrounds the solar system. This outer reservoir of comets, called the Oort cloud, extends roughly a light-year from the Sun in every direction and contains trillions of icy objects left over from the formation of the solar system. Most of those objects will never come near the inner solar system. But gravitational disturbances, whether from passing stars or from the denser material in a spiral arm, can nudge Oort cloud objects onto new paths, sending some of them plunging inward toward the planets. Some researchers have proposed that periodic increases in comet impacts on Earth may correlate with the Sun's passages through denser parts of the galaxy. The idea is not definitively established. The geological and fossil record is complex enough that drawing precise timing correlations is difficult. But the basic physics is real. Our position in the galaxy, even our specific position within the Orion Arm, is not simply a geographic fact. It may be part of a longer story about what life on Earth has experienced over billions of years. Where we happen to be in the Arm, relative to its densest regions and most active stellar complexes, has potentially shaped the history of the planet we live on in ways we're only beginning to piece together. The local bubble is one of the stranger features of our immediate galactic neighborhood, and most people have never heard of it. Our solar system doesn't sit in a typical region of the interstellar medium. We're inside a large, irregular cavity in the gas of the Orion Arm, a region where the density of interstellar material is substantially lower than in the surrounding areas. This cavity is called the local bubble. It spans roughly 1,000 light-years in its longest dimension, though the shape is irregular and its boundaries are gradual rather than sharp. The interior of the local bubble is filled with hot, thin plasma heated to temperatures of roughly 1,000,000 degrees. That sounds extreme. It is extreme. But this hot gas is also extraordinarily tenuous. There's so little material inside the bubble that despite its temperature, it carries almost no actual thermal energy by any human measure. The individual atoms are moving fast, as hot atoms do, but there are so few of them that they barely interact with anything. Temperature and heat are different things when densities are this low. The local bubble is thought to have been carved out by a series of supernova explosions over the past several million years. When a massive star ends its life in a supernova, the explosion releases an enormous amount of energy, blasting an expanding bubble of hot gas outward into the surrounding medium. Multiple supernovae in the same general region can create overlapping bubbles that merge into a single large cavity. Astronomers have traced the origin of the local bubble to a group of massive stars that lived and expired in this region over the past 10 to 20 million years. Their remnants, the neutron stars and black holes they left behind, have drifted away. But the cavity they carved is still here, and we're inside it. A study published in 2022 in the journal Nature used Gaia data to map the star-forming regions around the edge of the local bubble in striking detail. The researchers found something that, once you see it, is hard to unsee. Nearly every nearby molecular cloud, every active star-forming region within roughly 1,000 light-years of us, sits on or near the surface of the local bubble. The Taurus clouds, the Perseus clouds, the Ophiuchus region, clouds near the southern coal sack. All of them appear to lie along the expanding shell of material that the ancient supernovae pushed outward over millions of years. The researchers traced this shell's expansion back to its origin point and timing, concluding that the local bubble began expanding about 14 million years ago, driven by roughly 15 supernovae over that period. That sequence of ancient stellar explosions didn't just carve out the cavity we currently inhabit. It compressed the surrounding gas into dense shells that are now actively forming new stars, including the star-forming regions that were observable when modern humans first appeared on Earth, including regions that are still actively making new stars right now. The ancient deaths of massive stars, millions of years before our species existed, triggered the births of stars that are igniting at this moment. And we're living inside the bubble those deaths created. Understanding where we are inside the Milky Way required solving what turned out to be a genuinely difficult problem. You can't step outside the galaxy and look back at it. You're embedded in it, Trying to map the Milky Way's spiral structure from inside is like trying to map a city while standing blindfolded in the middle of a crowded park. You can tell there are buildings around you. You can tell some are close and some are distant. But seeing the full layout, the streets, the districts, the overall shape is extremely hard when you can't get above it to see the pattern. For most of the 20th century, astronomers used different wavelengths of light to try to peer through the dust of the Milky Way and trace its structure. Visible light gets blocked by interstellar dust relatively easily. The dust grains scattered through the disk absorb and scatter visible photons, which is why the band of the Milky Way you see, in a dark sky location, looks dense and cloudy rather than perfectly transparent. But radio waves pass through dust almost unimpeded. In the 1950s, astronomers used radio telescopes to map the distribution of neutral hydrogen gas in the Milky Way by detecting its characteristic emission at a wavelength of 21 centimeters. Hydrogen emits this specific wavelength when the spin of its single electron flips relative to its proton. It happens rarely for any individual atom, but hydrogen is so abundant that the cumulative signal is detectable across vast distances. This technique revealed the broad outlines of spiral structure in the Milky Way for the first time. Astronomers could see regions of higher gas density corresponding to spiral arms. They could trace the arms across the galaxy, or at least the portions visible from Earth. But the mapping was imprecise. The velocities of gas clouds told you their distance only if you made assumptions about how the galaxy rotates, assumptions that turned out to be not quite accurate in all directions. Infrared observations improved things considerably. Infrared light penetrates dust better than visible light, and by the 1990s and 2000s, infrared space telescopes were revealing star clusters and massive stars embedded deep in the disk that visible light surveys had missed entirely. The Spitzer Space Telescope, launched in 2003, conducted a major survey of the Milky Way in infrared wavelengths and produced detailed maps of the stellar populations in both the disk and the spiral arms. From Spitzer data, astronomers began to pin down the positions of the four major arms with more confidence. They could see star clusters that were previously invisible, massive young stellar objects hidden behind curtains of dust, and the overall shape of the disk with unprecedented clarity. But the real transformation came from astrometry. The precise measurement of the positions and motions of individual stars. The Gaia mission, launched by the European Space Agency in December 2013, was designed specifically for this purpose. Gaia measures the positions, distances, and motions of stars across the Milky Way with a precision that previous instruments couldn't approach. It does this using parallax, the apparent shift in a star's position as Earth moves around the Sun. When you hold your finger up in front of your face and close one eye, then the other, your finger appears to jump relative to the background. That's parallax. Stars are far enough away that the effect is tiny, but measurable if your instruments are good enough. Gaia's instruments are extraordinarily good. Its first major data release covered over 1 billion stars. Its subsequent releases added more, with improving precision at each step. The third major data release, in 2022, provided positions, distances, and motions for nearly 1.5 billion stars, reaching out to thousands of light-years in multiple directions with errors small enough to be scientifically meaningful. The effect on our picture of the Orion Arm was substantial. Previous estimates had the arm as a modest spur a few thousand light-years long. Gaia revealed coherent features, stretching many times that distance. The arm's physical extent and its width were both revised sharply upward. A study using Gaia data combined with observations of masers, compact sources of radio emission associated with massive star-forming regions, traced the Orion Arm structure across a baseline much longer than previously possible. The arm emerged from that analysis not as a minor connecting bridge, but as a substantial galactic structure in its own right. The fact that we spent most of the 20th century thinking we lived in something smaller says less about the arm and more about how hard the galaxy is to map from the inside. We were wrong. The neighborhood was bigger than we thought. It still is. The arm is filled with objects that reward, looking at individually, not just as statistics in a census. The Rosette Nebula sits about 5,200 light-years away in the constellation Monoceros. It's a ring-shaped cloud of glowing gas, about 130 light-years across, surrounding a young open star cluster at its center. The hot young stars in that central cluster are bombarding the surrounding gas with ultraviolet radiation, stripping electrons from hydrogen atoms and causing the cloud to glow in the characteristic deep red of ionized hydrogen. The rosette looks delicate when imaged from our distance. Up close, it's a violent place. The radiation from those central stars is so intense that it's actively carving away the surrounding cloud, driving stellar winds that sculpt the gas into intricate pillars and filaments before eventually dispersing it entirely. In a few million years, the rosette will be gone. The gas it's made of will either have condensed into new stars or been blown out into the interstellar medium. The cluster at its center will remain, drifting through the arm as its stars age and eventually spread apart. The Carina Nebula is one of the most dramatic features in the Orion Arm. It sits roughly 7,500 light-years away and spans about 300 light-years, making it larger than the Orion Nebula, despite being nearly 6 times more distant. The Carina Nebula contains some of the most massive and luminous stars known anywhere in the Milky Way, including Eta Carinae. It also contains the cluster NGC 3372, with dozens of O-type stars, the hottest and most massive stellar classification, pouring energy into the surrounding nebula at rates that reshape the gas over timescales of thousands of years. The James Webb Space Telescope has imaged the edge of the Carina Nebula in extraordinary detail, revealing dozens of previously unknown protostars and jets of material erupting from newly forming stellar systems. Star formation happening on a scale that dwarfs the Orion Nebula entirely. There's the Eagle Nebula, 6,500 light-years away, home to what is arguably the most famous image in the history of astronomy, the Pillars of Creation. The pillars are columns of dense gas and dust, each several light-years tall, that have been sculpted by the radiation and stellar winds from a young star cluster called NGC 6611 nearby. Hubble imaged them in 1995 and produced one of those photographs that entered the cultural consciousness so completely that anyone who's spent time thinking about space has seen it. The James Webb Space Telescope imaged them again in 2022 in infrared, revealing details invisible to Hubble, including newly forming stars embedded within the pillars themselves. The pillars are being eroded. The radiation from the hot stars nearby is slowly destroying them from the outside in. In roughly 100,000 years, the pillars will no longer exist. But the protostars forming inside them right now, if they complete their formation before the pillars dissolve, will survive and become part of the galaxy for billions of years. The pillars are making stars, even as they're being taken apart. There's the Lagoon Nebula, about 4,100 light-years away in Sagittarius, one of the few emission nebulae visible to the naked eye from a dark location. There's the Trifid Nebula nearby, roughly 9,000 light-years distant, unusual for its combination of emission, reflection, and dark nebula regions in the same object. There's the Omega Nebula, also called the Swan Nebula, at roughly 5,000 to 6,000 light-years, one of the most massive star-forming regions in the Milky Way. The Omega Nebula contains enough raw material to produce several thousand stars the size of the Sun. It's actively doing so. Each of these objects is a feature of the Orion Arm. Each one is active, dynamic, physically extreme in its own way. And each one is visible in principle, at least with the right instruments, from the surface of a small rocky planet sitting quietly inside the arm that contains them all. The Sun's position within the Orion Arm is not arbitrary from a habitability standpoint. Not that we chose it. We didn't. We're here because the processes that formed the solar system 4.5 billion years ago happened here. The particular cloud of gas and dust that collapsed to form the Sun and its planets was in this part of the arm at that time, and that's where we ended up. But the position turns out to have properties that may matter for a planet trying to sustain complex life over billions of years. We sit in a relatively quiet region of the arm, not inside a dense, active star-forming complex where intense radiation from nearby massive stars would bathe the solar system in levels of ultraviolet and X-ray energy that could make the surface of a planet deeply hostile. Not close to the galactic center, where stellar densities are so high that gravitational interactions between neighboring systems would frequently disrupt stable planetary orbits. Not in the outer edge of the galaxy, where the interstellar medium is so thin that the raw material for rocky planets, the elements heavier than hydrogen and helium that were forged and scattered by billions of years of previous stellar generations, would be too sparse to build Earth-like worlds. We're in a middle zone, far enough from the center to be in a relatively calm region where stellar encounters are rare, close enough to the center that the gas from which we formed had been processed through multiple previous generations of stars and was enriched with carbon, oxygen, nitrogen, silicon, iron, and all the other elements that make complex chemistry and rocky planets possible. The concept of a galactic habitable zone was formalized in the early 2000s. The idea is that a galaxy has a region, analogous to the habitable zone, around an individual star, where the conditions for complex life are most favorable. Too close to the galactic center means too much radiation, too many stellar encounters, too many nearby supernova events. Too far out means too few heavy elements and too sparse an environment. The Orion Arm sits in the proposed galactic habitable zone. Whether this constraint matters as much as the original models suggested is debated. More recent research suggests the galactic habitable zone may be broader than initially thought, that the inner boundary may not be as harsh as feared, and that life, if it exists elsewhere in the galaxy, may be more tolerant of a range of galactic environments than early models assumed. But the basic observation remains. We're in a part of the galaxy that isn't obviously hostile to the existence of complex chemistry and long-term planetary stability. The universe is mostly places where such conditions don't apply. The interior of a star, the surface of a neutron star. The interior of a molecular cloud, too cold and dense for anything but the simplest chemistry. The vast regions between galaxies where the density of matter is effectively zero. That we happen to be in a place where the temperature, density, radiation environment, and elemental composition are all within ranges compatible with biological complexity is a significant fact about our position in the cosmos, even if it's a fact we had no say in. The nearest stars to our Sun all sit within the Orion Arm. Proxima Centauri, the closest, is about 4.24 light-years away. That's roughly 25 trillion miles. It is, in every practical and engineering sense, unreachably far with any technology we currently possess or could build in the near future. Alpha Centauri A and B, the two Sun-like stars that make up the other members of the nearest star system, orbit each other at a distance that varies between roughly 11 and 36 astronomical units, and lie at essentially the same distance as Proxima. Barnard's star, a red dwarf about 6 light-years away, is the next nearest individual stellar system. Wolf 359, Lalande 21185. Sirius, the brightest star in the night sky, at about 8.6 light-years. Epsilon, Eridani, and Tau Ceti, which have long been of interest to astronomers looking for potentially habitable planetary systems. All within a few dozen light-years. All inside the Orion Arm. All separated from our Sun by distances so enormous that our fastest spacecraft would take tens of thousands of years to reach the nearest of them. And Proxima Centauri, the closest star we know of, is simply another point in the arm, not the edge of the arm, not a distant outpost, just a neighbor in the same local region of the same galactic structure. The stars, within about 325 light-years of the Sun, constitute what astronomers call the local stellar neighborhood. This region contains roughly 3,000 to 4,000 stars. Most of them are red dwarfs, dim and small, many probably hosting planets, almost none of them visible to the naked eye from Earth. Of those several thousand stars, only a handful are large and luminous enough to be detected without a telescope. The rest are invisible to unaided human vision. This matters more than it might seem. When you look up at the night sky and count stars, you might see 2,000 on a clear night from a reasonably dark location. All of those visible stars are within roughly a few thousand light-years. They're the bright, luminous, often young objects that outshine the countless dim ones surrounding them. The real population of the Orion Arm is dominated by stars you can't see without help. Red dwarfs outnumber Sun-like stars roughly 10 to 1 in the Milky Way. The same ratio holds in the Arm. For every Sun-like star you can point to in the sky, there are roughly 10 dim red dwarfs sitting near it that are completely invisible to you without a telescope. The Arm is full of these quiet, dim, long-lived stars. Some of them are billions of years older than our Sun. Some of them have been burning since the early universe, when the Milky Way itself was young and its structure was still taking shape. They're so conservative with their fuel that some will still be burning long after the Sun has completed its entire life cycle, expanded into a red giant, shed its outer layers, and cooled into a dark remnant. The dimmest red dwarfs may burn for trillions of years. Long after the universe is many times its current age. The interstellar medium within the Orion Arm is not empty space. Between the stars, between the molecular clouds, in the gaps that look featureless from any distance, there is material, gas and dust, at densities that vary enormously from place to place, but average roughly 1 atom per cubic centimeter throughout the disk of the galaxy. That is extraordinarily thin by any human standard. The best vacuum achievable in a laboratory on Earth still contains roughly 100 million times more atoms per cubic centimeter than the average interstellar medium. But scale changes everything. Across light years of distance, even this thin material adds up to something substantial. The interstellar gas is mostly hydrogen, about 74% by mass, with helium making up roughly 24%. The remaining 2%, the trace, is everything else. Carbon, oxygen, nitrogen, silicon, iron, calcium, sulfur, and dozens of other elements in various ionization states and chemical combinations. That final 2% is called the metals in astronomical terminology, a usage that confuses chemists who define metals more specifically. But in astronomy, anything heavier than helium qualifies. The dust mixed into this gas consists of microscopic solid particles, typically less than 1 micrometer in diameter, made of silicates, carbon compounds, and various ices. These dust grains do several things that matter enormously for the long-term behavior of the arm. They block starlight, which is why you can't see through the disk of the Milky Way in visible wavelengths. They provide surfaces where atoms can meet and stick together, enabling the formation of molecular hydrogen and more complex molecules that couldn't form in the gas phase. They absorb ultraviolet radiation from nearby stars and re-emit it as infrared, redistributing energy through the medium. And they're the raw seeds around which more complex chemistry builds up in the coldest, densest regions of molecular clouds. When a cloud collapses to form stars, those dust grains end up in the protoplanetary disk. They collide and stick together, grow from micrometers to millimeters, to centimeters to meters, to kilometers, slowly building the planetesimals that eventually become planets. Every rocky planet, including Earth, was built largely from material that was once interstellar dust grains, drifting quietly through the interstellar medium of the arm. The silicon and oxygen in the rocks beneath your feet were once microscopic grains floating through the space between stars. The iron in your blood was forged inside a massive star that lived and ended its life before our sun existed, scattered through the arm by a supernova explosion, and eventually swept up into the cloud that formed the solar system. The carbon in every molecule of every cell in your body went through cycles of stellar nucleosynthesis and interstellar chemistry before ending up as part of a living organism on a planet embedded in this arm of this galaxy. The arm isn't the background to our existence. In a very direct material sense, the arm is what we're made of. Let's look at what's happening inside the arm at this moment. Not the static picture of stars in their current positions, but the dynamic reality of a structure in ongoing motion and transformation. Stars in the Orion Arm are moving. Not just orbiting the galactic center together, but drifting relative to each other in all directions. The Sun is moving through the local stellar neighborhood at about 12 miles per second relative to the average motion of the nearby stars. This is called the solar apex motion. The direction the Sun is heading, the solar apex, is a point in the constellation Hercules. Over tens of thousands of years, this drift will carry the Sun to a meaningfully different position relative to its current nearest neighbors. Everything else is also moving. Barnard's star, at roughly 6 light-years distance, is crossing our sky faster than any other known star, a property called high proper motion. It's not just moving across the sky, it's also approaching the solar system. In about 10,000 years, it will reach its closest point of about 3.8 light-years from our Sun, temporarily making it the nearest star system to us, briefly displacing Proxima Centauri from that position before it continues moving away. Nearby stars have been closer to us than they are now, and they'll be closer again in the future. The local stellar neighborhood is not a fixed arrangement. It's a constantly shuffling collection of stars drifting past each other on timescales of thousands to millions of years. Stars in the Orion Arm are being born right now. In the molecular clouds of the arm, hydrogen gas is collapsing under its own gravity into new stars. The process takes tens of thousands of years, from the initial collapse of a cloud fragment to a star hot enough to ignite nuclear fusion at its core. In the Orion molecular cloud complex, there are hundreds of protostars in various stages of this process. Some have already switched on nuclear burning. Some are still gathering material from their surrounding envelopes. Some are surrounded by protoplanetary disks where solid material is beginning to clump together. It's possible that Earth-like planets are forming in the Orion Nebula right now. By the time the Sun has run through another billion years of its life, some of those protoplanetary systems will be mature. Stable solar systems, with their own histories, unfolding on their own timescales. Stars in the Orion Arm are also ending their lives. The most massive stars, the ones 10 or 20 or 100 times the Sun's mass, burn through their fuel in millions of years and end in supernovae. A typical large galaxy, like the Milky Way, experiences roughly one supernova every few decades. Most are hidden behind dust and not visible from Earth. But the physics doesn't care whether we can see them. Stars are ending in the arm right now. Stellar remnants are being created. Neutron stars spinning hundreds of times per second, emitting beams of radiation that sweep through space like cosmic lighthouses. Black holes, remnants of the most massive stars, sitting quietly in the interstellar medium, detectable only by their effects on surrounding gas or companion stars. The arm is not a stable, finished structure. It's an ongoing process. Material cycling through generations of stars, from gas to star, to supernova, to enriched gas, to the next generation of stars. That cycle has been running in this part of the galaxy for billions of years. It will continue running long after the Sun is gone. Betelgeuse deserves its own moment here. It's not a distant object. On galactic scales, it's practically next door, about 700 light-years away. In the constellation Orion, it marks the left shoulder of the Hunter, a red supergiant so enormous that if it replaced our Sun, its outer surface would extend past the orbit of Jupiter. Betelgeuse is in the late stages of its life. It's consumed the hydrogen in its core, moved on to helium, and is now burning heavier elements in nested shells around an increasingly dense, iron-rich center. Iron is the endpoint of stellar nucleosynthesis. You can extract energy by fusing elements lighter than iron together. You cannot extract energy by fusing iron. When a massive star builds an iron core, the core collapses. The collapse is so rapid and so energetic that the outer layers of the star are blasted away in a supernova. Betelgeuse is moving toward that moment. How soon is not known precisely. It could be in 10,000 years. It could be in 100,000 years. It could, in principle, be sooner. The star fluctuates in brightness irregularly, a sign of the instability that characterizes massive stars in their final phases. In December 2019 and January 2020, Betelgeuse underwent a dramatic dimming event fading to roughly 40% of its typical brightness. For a few weeks, it was dimmer than it had been in the modern era of careful astronomical observation. Speculation was immediate and widespread. Was it about to go supernova? It wasn't. The dimming was caused by a large mass ejection event in which the star expelled a substantial cloud of gas that then cooled and condensed into dust, temporarily obscuring the star's surface from our view. Betelgeuse recovered its brightness as the dust dispersed. But the episode revealed just how dynamic and unpredictable these massive stars are in their final phases of evolution. When Betelgeuse does finally go supernova, the event will be visible in daylight from Earth. It will cast shadows at night. It will appear as bright as the crescent moon. It will be, without any question, the most dramatic astronomical event in recorded human history. And it will be a feature of the Orion Arm. The death of a star that has been part of the Arm's stellar population for about 8 to 8.5 million years. Its core will be left behind as a neutron star, compressed into a sphere roughly 12 miles across, denser than an atomic nucleus, spinning rapidly and cooling slowly over billions of years. The outer layers will expand outward, creating a glowing supernova remnant that will be visible for thousands of years as it sweeps through the interstellar medium around it. Eventually, that material will mix back into the Arm's interstellar medium, enriched with the elements Betelgeuse produced during its life. Those elements will become part of the next generation of gas clouds, part of the next generation of stars, part of the next generation of solar systems. And the cycle continues. This cycle of stellar birth and death is not just a process happening around us. It's the process that made us possible. The Sun is a third-generation star, or possibly later. That designation means the gas from which it formed had already been processed through at least 2 previous generations of stars before being incorporated into our solar system. The first stars in the universe, sometimes called population 3 stars, formed from almost pure hydrogen and helium. There were no heavier elements. No carbon, no oxygen, no iron. Just the 2 lightest elements produced in the first few minutes after the Big Bang. Those first stars were likely enormously massive, far larger than any stars we see today, because the gas they formed from had no metals to cool it efficiently. And cooling is what allows gas clouds to fragment into smaller pieces. Without efficient cooling, the gas clouds collapsed into huge, massive stars that burned through their fuel rapidly and ended in supernovae within just a few million years. Those explosions scattered the first heavy elements into the universe. Carbon, oxygen, neon, silicon, iron, everything up through the Iron Peak, forged in the cores and expelled in the deaths of those first stellar generations. A second generation of stars formed from gas now enriched with these metals. Some of those stars also ended in supernovae, further enriching the interstellar medium. And so on, through multiple generations of stellar birth and death, each one adding to the reservoir of heavy elements available for subsequent stars and planets. By the time the Sun formed 4.6 billion years ago, the interstellar medium, in its part of the Orion Arm, had been processed through enough stellar generations that it contained roughly 2% heavy elements by mass. That was enough to build rocky planets. The Earth, Venus, Mars, Mercury, all the terrestrial planets in our solar system, were assembled from material that exists because of billions of years of stellar nucleosynthesis in this arm. If the Sun had formed earlier, in a less processed environment, the raw material for rocky planets might not have been available. If the Sun had formed too late, some of the remaining star-forming gas in the arm might have been used up. The timing and location of the Sun's formation within the arm matters. Not in a designed way, but in a physical, consequential way that traces back through multiple generations of stellar history. Positioning ourselves on a map of the Milky Way is one thing. Actually grasping what the numbers mean requires something more. Let's try to get at it from a different direction. The fastest human-made object in the history of spaceflight was the Helios 2 solar probe, which, at its closest approach to the Sun, reached speeds of about 157,000 miles per hour, driven by the Sun's gravity as it swooped inward. This remains the speed record for anything we've built. At that velocity, traveling from Earth to the Moon would take less than 2 hours. Traveling from Earth to the Sun would take about 25 days. Traveling to Pluto, at its average distance from the Sun, would take roughly 2.5 years. Now, take that speed and point it at the nearest star. At 157,000 miles per hour, reaching Proxima Centauri would take about 19,000 years. 19,000 years. The first permanent human settlements hadn't appeared yet 19,000 years ago. There was no agriculture, no writing, no cities, no metal tools. The last glacial maximum had just ended. A probe launched at that moment, at the fastest speed any human object has ever achieved, would still be traveling through interstellar space right now. It wouldn't have arrived yet. And Proxima Centauri is the closest star we know of. The Orion Arm extends thousands of times farther than that. The Arm is not a place we are going to cross. It's not a place we are going to explore in the way we explore a continent. It is simply the context of our existence, vast beyond any practical meaning of that word, and we are embedded in one small, quiet corner of it. What's remarkable is not that we're small. What's remarkable is that we know any of this. The question of whether the Orion Arm hosts other life is, in many ways, the most important question embedded in everything we've covered. The Arm contains billions of stars. Around most of those stars, we now know from the Kepler Space Telescope survey and subsequent missions, there are planets. Kepler surveyed a sample of roughly 150,000 stars and found that planet formation is not rare. It appears to be the default outcome of star formation. Most stars have planets. The fraction of Sun-like stars with rocky planets in the approximate habitable zone is estimated somewhere between 10 and 40%, depending on the specific definition of habitable zone and which stellar types are included in the calculation. Even at the lowest end of that estimate, the number of potentially habitable rocky worlds in the Orion Arm alone is enormous. Hundreds of millions, at minimum. Possibly billions. That doesn't mean they all have life. We have exactly one data point for the emergence of life, and we don't fully understand how it happened even on our own planet. The chemistry of the first cell, the path from complex organic molecules to self-replicating systems, is still one of the deepest unsolved problems in science. The origin of life may require conditions far more specific than simply having a rocky planet with liquid water. Or it may be robust enough to emerge under a wide range of circumstances. We don't know. But the sheer number of candidate worlds within just this one arm of just this one galaxy means that even if the probability of life emerging on any given habitable world is extremely small, the expected number of worlds in the arm where life has emerged is still potentially substantial. The search for signatures of biology in the atmospheres of nearby exoplanets is underway and accelerating. The James Webb Space Telescope is analyzing the atmospheric chemistry of rocky planets orbiting nearby stars, looking for combinations of molecules that would be difficult to explain without a biological source. Oxygen, combined with methane, is one such signature. In a world without biology, these two gases react with each other and don't accumulate. Their simultaneous presence in an atmosphere requires something continuously replenishing them against chemical equilibrium. Life is the obvious candidate. The TRAPPIST-1 system, about 40 light-years from Earth, is comfortably within the Orion Arm and has attracted intense scientific attention since its discovery. It contains 7 rocky planets, 3 of which orbit in the habitable zone of their central red dwarf star. TRAPPIST-1 is a red dwarf, so cool and dim that its habitable zone lies extremely close in. The planets there are tidally locked, with one hemisphere permanently facing the star and the other in permanent darkness. The red dwarf also produces frequent, intense flares. Whether those conditions support or suppress life, whether the radiation environment is too harsh for surface biology but potentially hospitable in the oceans of tidally locked worlds, whether the lack of a day-night cycle makes complex climate dynamics impossible or merely different, are all active research questions. We don't have the answers. We are building the instruments and accumulating the data that might eventually provide them. Within the next decade or two, barring catastrophic disruption to scientific infrastructure, we will have the first genuinely informative observations of rocky exoplanet atmospheres. The answer to whether we're alone in the Orion Arm may not be far off. And either answer will be the most significant scientific result in history. Finding evidence of life elsewhere in the Arm would transform everything we think we understand about our place in the universe. Finding that the Arm is otherwise empty, despite billions of candidate worlds, would raise questions about the nature of life and its emergence that would drive science for generations. Neither outcome is quiet. There's another way to understand our position in the Orion Arm that doesn't involve distances or luminosities. It involves time. The Arm has existed, in roughly its current form, for hundreds of millions of years. Our solar system has been part of it for about 4.6 billion years. Life on Earth has existed for at least 3.8 billion years. Complex, multicellular life has existed for roughly 540 million years. Our genus, Homo, appeared roughly 2 to 3 million years ago. Modern humans, our specific species, appeared roughly 300,000 years ago. The first written records we have extend back about 5 to 6,000 years. We have been doing modern science with careful observation, measurement, mathematics, and the systematic testing of ideas for perhaps 500 years, depending on where you draw the line. We have been doing astronomy, capable of reaching beyond the nearest stars for roughly a century. We have been doing astrometry, capable of mapping the Orion Arm's actual structure for perhaps 30 years. The Gaia mission, which has done more to reveal the Arm's true extent than anything before it, is still operating. Its most detailed data releases are still being analyzed. The picture we have of the Orion Arm in the year 2026 is the most accurate picture that has ever existed, and it's still incomplete. We are at the very beginning of understanding the structure we live in. The Arm has been here for far longer than our species has existed. It will be here for far longer than our species is likely to exist. And we have been looking at it carefully for a time so small that it barely registers against the arm's own history. A few decades of precise astrometry. A few decades of infrared and radio mapping against hundreds of millions of years of the arm's own existence. And yet, in those few decades, we've gone from thinking we lived in a minor spur to understanding we live in a substantial galactic structure, tens of thousands of light years long, filled with billions of stars, containing countless regions of active star formation, hosting billions of candidate worlds, shaped by supernova events millions of years before our species appeared, and sitting inside a bubble those ancient explosions created. That's the pace of what we're doing. That's what a century of careful looking has revealed. Imagine what the next century brings. There are places inside the Orion Arm we know almost nothing about. Not because they're particularly distant. Some of them are only a few thousand light years away. But they're embedded in regions where the dust is thick enough to block visible light almost completely, making observation in optical wavelengths nearly impossible. The galactic plane, in the direction of the center, is one such region. Towards Sagittarius and Scorpius, the interstellar dust lanes are so dense that visible light from objects more than a few thousand light-years away is absorbed almost entirely. To see into those regions, you need radio telescopes, infrared telescopes, or X-ray observatories, each of which penetrates dust differently and reveals different populations of objects. The ALMA Observatory, the Atacama Large Millimeter Array in Chile, is particularly powerful in this regard. ALMA observes at millimeter and sub-millimeter wavelengths, which penetrate dust effectively and reveal the cold, dense molecular gas in star-forming regions. It has imaged protoplanetary disks around forming stars in stunning detail, including disks with gap structures that suggest planets are already forming within them. It has detected complex organic molecules in molecular clouds, including compounds that are building blocks of the chemistry of life. Not evidence of life. Evidence that the raw materials of life's chemistry are distributed through the arm's molecular clouds. This is a significant distinction that matters a great deal. Amino acids, the building blocks of proteins, have been detected in meteorites that fell to Earth. They've been detected spectroscopically in molecular clouds. They form readily in laboratory experiments, simulating interstellar conditions. The molecular complexity needed to get from raw elements to life is not the hard part. The chemistry happens readily, under a wide range of conditions. What we don't understand is the transition from complex chemistry to self-replicating biological systems. That transition, wherever it happened on Earth, and however long it took, is the gap we can't yet bridge in our understanding. But the arm is full of the ingredients. The question of assembly is the one we don't have the answer to. There's a final aspect of the Orion Arm that matters and that rarely gets discussed. Our position in the arm relative to the galactic plane. The Milky Way's disk is not perfectly flat. It has a slight warp, a gentle bending that becomes more pronounced toward the outer edges of the galaxy. Within the disk, individual stars, star clusters, and molecular clouds sit at different heights above and below the theoretical midplane. The Sun is currently located very close to the midplane, slightly above it by roughly 80 light-years, which is negligible on the scale of the disk's full thickness of several hundred to 1,000 light-years. But the Sun oscillates up and down through the galactic plane over time. The period of this oscillation is roughly 60 to 70 million years. The Sun bobs up above the midplane, slows, reverses, passes back through, goes below, and returns. At its maximum excursion, it reaches a few hundred light-years above or below the midplane. During the parts of this cycle where the Sun is near the midplane, it's in the densest region of the disk, with the highest concentration of stars, gas, and dust. During the parts where it's furthest from the midplane, it's in a thinner, less dense environment. This oscillation has been proposed as another factor in the long-term history of life on Earth. When the solar system is near the midplane, it passes through more dense material, potentially triggering more gravitational perturbations of the Oort cloud and sending more comets toward the inner solar system. Whether this translates into measurable patterns in impact rates or extinction events is debated and not clearly established in the geological record. But the fact that our position in the arm is three-dimensional, not just a point on a two-dimensional map, and that this position changes over time in multiple ways, is part of the full picture of where we are and what that means for the history of our planet. We are not fixed in place. We're moving in three dimensions relative to the structure around us, through a dense and active part of the galaxy, oscillating through the midplane, slowly drifting relative to our stellar neighbors, making one slow circuit of the galactic center every 225 million years. Everything is in motion. The Orion Arm is not a container we sit still inside. It's a dynamic structure we're moving through, and the details of that motion have had real consequences for the world we inhabit. The Gaia satellite is still collecting data. It will continue refining its map of the Milky Way's stellar population for years to come. Each successive data release has sharpened the picture. The third major release, in 2022, was transformative. The fourth, when it comes, will be more so. New radio telescope arrays are mapping the Milky Way in radio wavelengths with resolution that would have been inconceivable a generation ago. The Square Kilometre Array, an international project that will eventually link thousands of individual radio dish receivers across South Africa and Australia, will have the sensitivity to detect signals from across the galaxy that current instruments cannot reach. The next generation of extremely large optical telescopes, ground-based mirrors 30 to 40 meters in diameter, will be able to observe fainter stars at greater distances and with more spectral detail than anything currently operational. These instruments will fill in the map of the Orion Arm in ways we can't fully anticipate, because history suggests that new instruments reveal not just more of what we expected, but also things we weren't looking for. Every time we've built a telescope with significantly improved sensitivity or resolution or wavelength coverage, it has found things that weren't in the previous models. X-ray telescopes revealed populations of compact objects no one had predicted in the numbers observed. Infrared telescopes revealed star-forming regions hidden behind dust that optical surveys had missed entirely. Radio telescopes revealed pulsars, fast radio bursts, and molecular clouds full of complex chemistry that nobody had anticipated. Gravitational wave detectors revealed a merger rate of compact binary systems that exceeded some theoretical estimates. The next generation of instruments will do the same. They will show us something about the Orion Arm that we don't know to expect. That's not a guess. It's a pattern that has held consistently across every significant improvement in observational capability in the history of astronomy. The Arm has more in it than we currently know. It always has. Every photon that reaches a telescope on Earth has traveled through the Orion Arm to get here. The light from the Carina Nebula, from the molecular clouds of Ophiuchus and Taurus, from the glowing ring of the Rosette, from the ancient red light of distant giant stars. All of it has passed through the same thin gas, and drifting dust grains that surround us. Through the same local bubble, through the same local neighborhood of nearby stars. It arrives at mirrors and lenses built by human hands, gets focused onto detectors designed by human minds, and produces data that human intelligence then interprets using mathematics accumulated over centuries of effort. The arm sends out light. We built the instruments to catch it. We developed the mathematics to read what it says. That exchange, light from the arm, received and decoded by something inside the arm, is one of the more remarkable things that has happened in the roughly 225 million years. The Milky Way has taken to complete its most recent rotation. The arm doesn't know we're here. It doesn't have opinions about us. It doesn't register our presence in any physical sense. But we know it's here. We've mapped it. We've traced its length and width, measured the positions of its billion stars, dated the ages of its molecular clouds, traced the bubble carved into its gas by ancient supernovae, detected the chemistry forming in its coldest regions, imaged the protoplanetary disks coalescing around its newest stars. We have, against all reasonable expectation, from our position on a small rocky planet around an average star, looked out at the structure we live inside and begun to understand it. The scale of the Orion Arm is not an abstraction. It is the actual size of the structure that contains every star visible to the naked eye from Earth's surface. Every star within reach of any spacecraft we have ever launched or could launch in the foreseeable future. Every stellar neighborhood we might ever hope to visit. It is, in every practical sense, the extent of the reachable universe for our species, at least with any technology we can currently conceive. We talk about the Milky Way sometimes as if it's a neighborhood. We talk about other galaxies as though they're distant destinations rather than effectively unreachable. The honest picture is that the Orion Arm alone is so large that we have barely scratched its edge. Voyager 1 crossed the heliopause in 2012, entering interstellar space for the first time. It's now roughly 15 billion miles from the Sun. That sounds immense. Against the length of the Orion Arm, it amounts to nothing measurable. A probe that has been traveling for nearly 50 years is still so close to where it started that on any map of the arm drawn to scale, its journey wouldn't show up. We are not leaving this arm in any meaningful technological time frame. We're not leaving the local stellar neighborhood in any meaningful technological time frame. We are here, in this arm, around this star, on this planet. And there is something to be said for taking that in, not as a source of despair, but as a source of genuine orientation. We live inside one of the most dynamic, most structurally complex, most materially rich features of one of the larger spiral galaxies in the observable universe. A region where stars are being born in molecular clouds a few hundred light years away, where ancient supernova remnants have shaped the cavity we inhabit, where billions of candidate worlds orbit billions of stars across tens of thousands of light years, where one of the most violent stars in the local galaxy is building slowly toward an explosion that will be visible in daylight from Earth, where the James Webb Space Telescope is right now, imaging protoplanetary disks and molecular cloud chemistry and the atmospheres of rocky worlds orbiting nearby stars. We haven't finished mapping this place. We haven't come close to understanding everything in it. We've been looking carefully for perhaps a century, with instruments capable of measuring its actual structure for only a few decades. The arm has been here for hundreds of millions of years. It will be here for hundreds of millions more. And what we're doing right now, tonight, this moment, is part of the first tiny fraction of the arm's history, in which something inside it has looked back at itself and tried to understand what it's part of. Not a godlike perspective from outside, from inside, with instruments and mathematics, with patience and precision, with human minds that evolved on one small world around one ordinary star and figured out how to read the light coming from everywhere else. That's not small. That's the opposite of small. The Orion Arm is tens of thousands of light years long. It's been here since before the dinosaurs. It will be here long after the sun is gone. And it took until right now, in the brief, unlikely history of this particular planet, for something in the arm to look up and see it. That's what we've been doing. That's what you're doing right now. Sitting wherever you are, thinking about a structure so large that your entire species fits inside one negligible corner of it without even noticing the walls. And yet, you know it's there. You know approximately where you are in it. You know something about what it contains, what's happening inside it, what shaped it, what's still shaping it now. The universe gave you a small planet around an average star in a minor arm of an ordinary galaxy, and you turned that into a map. The arm has structure on scales we're still learning to see. Not just the large features, the star-forming complexes, the molecular clouds, the young stellar associations, but structure on smaller scales too. Clusters of stars that form together from the same cloud and have been slowly drifting apart over millions of years. Moving groups, collections of stars that share a common velocity through space, even though they're now spread over hundreds of light years. Remnants of ancient clusters that have been tidally shredded by the galaxy's gravity over hundreds of millions of years. Streams of stars tracing paths through the local arm that reflect the history of past encounters between clouds and density waves. The Pleiades cluster, the Seven Sisters, is one of the most recognizable objects in the winter sky. It sits about 440 light-years away and contains several hundred stars, the brightest of which are young, hot blue stars burning with a luminosity hundreds of times greater than the sun. The Pleiades formed about 100 million years ago from the same cloud of gas. They're still loosely bound together, but gravity is slowly pulling them apart. In a few 100 million years, they'll have dispersed entirely into the general stellar field. The Hyades cluster, only about 150 light-years away, making it the nearest open cluster to the solar system, is older, roughly 625 million years, and more, spread out. It's the definitive example of a dispersing cluster in the local neighborhood, the reference standard against which stellar ages and distances have been calibrated for over a century. The Hyades were critical to establishing the distance scale for nearby stars in the early 20th century, at a time when the tools for measuring stellar distances precisely were still being developed. These clusters are not just pretty objects in the sky, they're data points. Each one encodes information about the history of star formation in the Orion Arm, about how gas clouds collapse and fragment, about how young stars interact with and are shaped by their environments, about the timescales over which structures form and disperse. By mapping clusters of different ages and tracing their origins, astronomers can reconstruct something like a partial history of star formation in our local region of the Arm over the past billion years. It's incomplete. Clusters older than a few billion years have almost entirely dispersed, leaving behind no obvious remnant. But for the last few 100 million years, the record is there in the positions and velocities of stars moving through the local neighborhood. a record written in the trajectories of suns. The physical conditions in different parts of the Orion Arm vary enormously, not just in stellar density or the presence of molecular clouds. The radiation environment, the magnetic field strength, the velocity dispersion of the gas, the temperature of the different phases of the interstellar medium, all of these change as you move through the arm. The interstellar medium is not a single uniform substance. It exists in several distinct phases, coexisting in rough pressure equilibrium. There's the cold neutral medium, dense regions of atomic hydrogen at temperatures of around 100 degrees above absolute zero, concentrated in thin sheets and filaments. There's the warm neutral medium, less dense atomic hydrogen at temperatures of roughly 8,000 degrees. There's the warm ionized medium, a diffuse plasma of ionized hydrogen at similar temperatures, filling a substantial fraction of the disk volume. And then there are the hot ionized regions, very tenuous plasma at temperatures of millions of degrees, like the interior of the local bubble, filling the largest volume but containing relatively little mass. These phases are not cleanly separated. They blend into each other. Cold, dense clumps of gas sit inside warmer, more diffuse envelopes. Hot bubbles from supernovae expand into warm gas. The interfaces between phases are sites of complex chemistry and physics. Understanding how these phases interact, how gas flows between them, how supernovae and stellar radiation maintain the balance, is one of the ongoing challenges of theoretical astrophysics. The balance between these phases shapes which parts of the arm can form stars and which cannot. Star formation requires cold, dense gas. Gas that has been heated by a nearby supernova or stripped of its dust by ultraviolet radiation can't collapse efficiently. The distribution of hot, warm, and cold gas in the arm determines where the next generation of stars will form, and that distribution is shaped by the stars that already exist through their radiation, their winds, and their eventual deaths as supernovae. The arm is self-regulating in a rough sense. Too much star formation in one region produces so many massive stars that their combined radiation and explosions heat and disrupt the surrounding gas, suppressing further star formation until the gas cools and recondenses. It's a feedback system operating on timescales of millions of years, across hundreds of light years, governed by the same physics that operates in a pot of boiling water, just slower and much, much larger. The Orion Arm contains a specific population of objects that give astronomers access to the arm's history in a way that stars alone cannot. Planetary nebulae. When a star like the Sun reaches the end of its main sequence life, it swells into a red giant, shedding its outer layers in a slow, extended process over hundreds of thousands of years. The shed material forms a glowing shell of ionized gas around the exposed stellar core, called a planetary nebula, a name that's genuinely confusing because it has nothing to do with planets. The name came from early telescopic observers who thought these round, glowing objects resembled the disks of planets. They don't, but the name stuck. The central remnant of a planetary nebula is a white dwarf, the dense, hot core of the former star, cooling slowly over billions of years. White dwarfs are one of the endpoints of stellar evolution for stars in roughly our mass range. They're typically about the size of Earth, but contain roughly the mass of the Sun, making them extraordinarily dense. A teaspoon of white dwarf material would weigh several tons on Earth's surface. There are thousands of known planetary nebulae in the Orion Arm. The Helix Nebula, about 650 light-years away, is one of the closest to Earth. It looks like a giant cosmic eye when imaged by telescopes, a ring of glowing gas about 2.5 light-years across, surrounding the white dwarf at its center. The Ring Nebula in Lyra is about 2,300 light-years away, a smaller but remarkably symmetrical shell of gas around its central remnant. The Cat's Eye Nebula, at about 3,000 light-years, has a complex, layered structure suggesting multiple mass loss events as its progenitor star-shed material. Each of these objects is the remnant of a stellar life. Each one encodes information about the mass, composition, and final evolution of its progenitor star. By studying the chemical compositions of planetary nebulae at different distances across the arm, astronomers can map how the arm's elemental composition has changed over time. The pattern they find confirms the picture. Older stars, formed earlier in the galaxy's history from gas that had been processed through fewer stellar generations, have lower metallicities. Younger stars, formed more recently from gas enriched by billions of years of prior stellar evolution, have higher metallicities. The arm has been getting progressively more metal-rich over time as generations of stars live and end and scatter their products back into the interstellar medium. We exist near the end of that enrichment process, at least on the timescale of the current universe. Later, generations of stars will be more metal-rich still. Eventually, the increased metallicity will begin to affect planetary formation, the chemistry of stellar atmospheres, even the internal processes of stellar evolution in ways that differ slightly from what we see in the current population. The arm is not static on any timescale. Even its chemical composition evolves. The interstellar magnetic field runs through the Orion Arm at a field strength of a few microgauss. That's extraordinarily weak by any human standard. A refrigerator magnet produces a field roughly 1,000,000 times stronger. But the magnetic field of the interstellar medium has an enormous effect on the behavior of gas and cosmic rays over the vast scales of the arm. Magnetic fields thread through the gas and dust of molecular clouds, providing pressure that helps support clouds against gravity and regulates the rate at which they collapse to form stars. The field lines channel the flow of ionized gas along specific directions, creating structure in the interstellar medium that would be absent without magnetism. Cosmic rays, high-energy charged particles, accelerated to near-light speed by supernova shocks and other energetic processes, are deflected by the magnetic field as they travel through the arm. This bending of their paths is what makes it impossible to directly trace cosmic rays back to their sources. By the time a cosmic ray reaches Earth, it has followed such a twisted path through the magnetic field that the direction it arrives from carries no information about where it came from. But the cosmic rays themselves are important. They carry energy into molecular clouds, providing a source of ionization that helps regulate the chemistry inside cold, dense regions that would otherwise be shielded from ordinary starlight. This ionization affects the rate of chemical reactions in the cloud, influencing which molecules form and in what quantities. The chain from supernova to cosmic ray to molecular cloud chemistry to planetary atmosphere chemistry is real, physical, and consequential. Even at the distance of molecular clouds, 1,000 light-years away, the deaths of massive stars affect the chemistry of the gas that will eventually form new solar systems. The arm is not a collection of isolated objects. It's a network of physical processes connected across vast distances by light, radiation, magnetic fields, cosmic rays, stellar winds, and the slow drift of gas and dust through the interstellar medium. Everything in it influences everything else. Just slowly. Just across distances that dwarf anything we can practically navigate. One of the more striking perspectives on the Orion Arm comes not from looking out into it, but from looking at how it appears from outside. We can't observe the Milky Way from outside, of course. But we can study other galaxies that are similar to ours and look at how their spiral arms appear and behave. The Andromeda Galaxy, about 2.5 million light-years away, is the nearest large spiral galaxy to the Milky Way. It's a barred spiral of similar size, though perhaps slightly larger than the Milky Way in some estimates and slightly smaller in others. Andromeda's spiral arms are visible in detailed images as bright, irregular structures lit up by the blue-white light of young massive stars and the red glow of ionized gas clouds. They're not neat, perfectly symmetric spirals. They're clumpy, irregular, with regions of intense star formation separated by gaps. The Milky Way's arms presumably look similar from outside. The Pinwheel Galaxy, also known as Messier 101, about 21 million light-years away, is a nearly face-on spiral galaxy that gives an excellent view of what a grand design spiral looks like from a perpendicular angle. Its major arms are clearly defined, winding outward from the central disk in a pattern that sweeps for tens of thousands of light-years. Embedded along those arms are brilliant pink-red regions of ionized hydrogen, equivalent to the Orion Nebula and Carina Nebula in our own arm, visible even at 21 million light-years distance because of their luminosity. The Orion Arm of the Milky Way would appear, from outside, as one of these bright features. Not the most prominent, because it's a minor arm, but visible, lit up by its young blue stars and glowing nebulae, present in the structure, contributing to the overall spiral pattern that an outside observer would see. There's something in that perspective worth considering. The light that would represent the Orion Arm to an outside observer has already left. It left millions of years ago, long before our species existed. An observer in a distant galaxy looking at the Milky Way right now is seeing us as we were millions of years before we appeared. And yet, the light leaving the Milky Way at this moment, the light that carries information about the current state of the Orion Arm, the current stars, the current nebulae, the current planets, will reach that distant galaxy millions of years from now. By the time that light arrives, if anything is there to receive it, both the Milky Way and the Orion Arm will look different again. The arm's current population of young blue stars will be gone, their lives too short to survive the crossing time. New stars will have formed in their place. The arm's molecular clouds will be in different states of collapse and dispersal. Betelgeuse will have gone supernova long before any of that light reaches a distant galaxy. Time and distance are the same thing at these scales. The formation of the solar system 4.5 billion years ago happened at a specific moment in the Orion Arm's history. The arm itself, in some form, is thought to have existed for several billion years at least. It was part of the Milky Way long before the Sun formed. When the gas cloud that eventually became the Sun began to collapse, the arm was already populated with billions of other stars, many of which no longer exist. Stars that formed 1 billion years before the Sun have already completed their entire lives. The most massive ones ended as supernovae, enriching the gas that would eventually form the Sun and planets. The less massive ones became white dwarfs that are still cooling quietly in the arm today, invisible remnants of stellar generations that came and went before Earth existed. The arm the Sun formed in 4.5 billion years ago was a mature structure with a complex history already behind it. And the arm the Sun is drifting through today is 4.5 billion years older than that. More stars have ended. More material has been cycled through stellar generations. The elemental composition of the interstellar medium has continued to evolve. More planetary systems have formed, matured, and in some cases been destabilized by stellar encounters or the deaths of their central stars. The history of life on Earth, from the first simple cells to the first complex animals to the first civilizations to this moment right now, has played out inside an arm that has been changing continuously throughout. The arm doesn't pause for us. It doesn't hold still. It continues its cycles of birth and death and chemical enrichment on its own timescale, which has nothing to do with ours. We are passengers in something that has been running for billions of years and will continue running after everything currently alive on Earth is gone. Passenger isn't quite the right word. We are, literally, made of it. We carry its history in the atoms of our bodies. Every heavy element in every human being was forged in the Orion Arm over billions of years, in the cores of stars that lived and ended before our sun existed. The arm made us, and we're inside it, and we're now looking at it and trying to understand what happened. That's an unusual situation for the universe to have arrived at. It doesn't happen everywhere. It may not happen often. But it's what's happening here. There are things about the Orion Arm we're still actively trying to figure out. The exact length of the arm remains somewhat uncertain, with different measurement methods giving different answers. Radio observations of masers, precise tracers of massive star-forming regions, give one picture. Optical and infrared observations of star clusters give another. The two aren't always perfectly consistent. This isn't a failure of the science. It's a reflection of the arm's genuine complexity. The arm doesn't have sharp, well-defined edges. It tapers and blends into the regions between arms. Different tracers highlight different aspects of the arm's structure. Young, massive stars glow brightly and trace the most actively star-forming regions. Older stars, less luminous on average, fill in the broader distribution. The arm defined by its most luminous young stars doesn't perfectly match the arm defined by its full stellar population. Both definitions are valid. They're tracing different aspects of the same structure. Similarly, the connection between the Orion Arm and the surrounding major arms, specifically how it connects to the Perseus Arm on one side and where its other end terminates or transitions, is still being mapped and debated. Some analyses suggest the Orion Arm extends further than previously thought, potentially merging with or connecting to other features in ways that make the designation minor arm increasingly awkward. The language of major and minor arms reflects a classification system developed before we had good enough data to see the arm's full extent. The data is still coming in. The Gaia mission continues. New radio surveys are underway. The picture is still filling in. What we know right now is dramatically more than what anyone knew a generation ago. And what we'll know a generation from now will be dramatically more than what we know right now. That's the honest state of the science. Not uncertainty as a failure. Uncertainty as the signature of an active, ongoing process of discovery. The arm we live in is not particularly special compared to the arms of other similar galaxies. It's not the most dramatic star-forming region in the Milky Way. The Sagittarius Arm, closer to the galactic center, contains more massive star-forming regions and more dramatic molecular clouds. The Scutum Centaurus arm, one of the two major arms of the galaxy, is physically grander in scale. The Perseus arm, the other primary arm, stretches for greater distances. By any objective measure of size or star formation rate or raw drama, the Orion Arm is not the most impressive arm in the galaxy. It's where we happen to be. That circumstance is enough to make it the most studied arm in the galaxy, simply because it's ours. We've mapped the local stellar neighborhood in the Orion Arm in more detail than any other comparable region of the Milky Way. We know the positions, distances, temperatures, chemical compositions, ages, and motions of stars within a few thousand light-years of the Sun in greater detail than we know any corresponding region of the Sagittarius or Perseus arms. This detailed knowledge of our local environment is not just a side effect of proximity. It's scientifically valuable in ways that extend beyond the arm itself. The physics operating in the Orion Arm is the same physics operating in every other arm of every other spiral galaxy. The laws of gravity, thermodynamics, nuclear physics, electromagnetism, fluid dynamics are universal. What we learn about the processes of star formation, stellar evolution, and interstellar medium physics by studying the Orion Arm in detail applies to spiral galaxies across the observable universe. We study it closely, partly because we can. And what we learn from it teaches us about everything else. The Andromeda Galaxy is approaching the Milky Way. This is a well-established fact of observational astronomy, and it has implications for the long-term future of the Orion Arm that are worth considering. Andromeda is currently about 2.5 million light-years away and moving toward the Milky Way at roughly 110 miles per second. In about 4 to 5 billion years, the two galaxies will merge. The merger won't be a collision in the usual sense. Galaxies are mostly empty space. When they merge, the individual stars almost never actually strike each other. What happens instead is a complex gravitational interaction that disrupts the orbital patterns of both galaxies, scatters stars into new trajectories, triggers waves of star formation as gas clouds are compressed by the interaction, and eventually, over a period of billions of years, assembles the two spiral galaxies into a single larger elliptical galaxy. This merged galaxy already has a nickname among astronomers: Milkomeda. When Milkomeda forms, the Orion Arm as a distinct structure will no longer exist. The spiral structure of the Milky Way will be disrupted by the merger. The arms will be torn apart. The stars within them, including our Sun and its planets, will be scattered into new orbits around the combined gravitational center of the merged galaxy. But before that happens, a different fate awaits the Sun. The Sun will exhaust its hydrogen fuel in about 5 billion years. When that happens, it will swell into a red giant, expanding its outer layers out past the current orbit of Earth. Whether Earth's surface survives in any recognizable form is uncertain and probably grim. The Sun will then shed its outer layers, exposing its hot core as a white dwarf, and spend the remainder of time cooling slowly in the interstellar medium. By the time the merger with Andromeda is complete, the Sun will already be a cooling white dwarf. What's inside the Orion Arm right now will outlast us. The Arm's red dwarf stars, burning slowly and conservatively, will survive for tens to hundreds of billions of years after the Sun is dark. They'll be scattered into the merged Milkomeda galaxy, losing their identity as members of the Orion Arm, but continuing their quiet hydrogen fusion for timescales that are genuinely difficult to comprehend. The atoms in those red dwarf stars, in the planets that may orbit them, in any chemistry that may have developed on those worlds, will still exist long after every structure we currently recognize in the Milky Way has been dissolved into the merged system. The Orion Arm has a finite future, but its constituent stars have futures that extend far beyond anything the arm itself will last to see. There's a simpler truth underneath all the numbers and distances and timescales. We don't fully understand what we're inside. We know more about the Orion Arm now than at any previous point in history. We know its approximate length, its width, its star-forming regions, its history, its chemistry, its future. But the knowledge is incomplete in ways that we're still discovering. Every new instrument reveals new questions. Every new survey finds structure that wasn't in the previous models. The Gaia mission was designed with specific scientific goals in mind. It found all of those and more. It also found things nobody was explicitly looking for. Stellar streams that had been invisible to previous surveys, revealing ancient galactic merger events buried in the motions of stars. Substructure in the distribution of stars that traces back to dynamical processes billions of years old. The Gaia data is still being analyzed. Papers are still being published from its most recent releases. The survey's final data release, when it comes, will be the most detailed picture of the local Milky Way's stellar population ever assembled. And it will still be incomplete. Because even Gaia's billion-star catalogue covers only a fraction of the total stellar population of the Orion Arm, weighted heavily toward the brighter, more easily measured objects. The dim red dwarfs, which outnumber sun-like stars significantly, are underrepresented in any optical survey. The full census of stars, in even the local stellar neighborhood, within 100 light-years of the Sun, is still not complete. Every few years, astronomers announce new nearby star systems that previous surveys had missed because they were too dim. There are almost certainly red dwarf systems within 20 or 30 light-years of Earth that haven't been identified yet. Not because we're not looking, because they're so faint that they're difficult to detect even from very close by on cosmic scales. The universe is more thorough than our instruments, and the arm is no exception. The language we use for the Orion Arm sometimes implies more certainty than exists. We talk about the arm's length of 25,000 light-years as though that's a precisely measured number with small error bars. It isn't. Different studies using different tracers and different methodologies give answers that vary by several thousand light-years. The arm's length, along different directions from the Sun, toward and away from the galactic center, and along the arm's long axis, are measured with different uncertainties. The connections between the Orion Arm and other structures in the Milky Way, specifically where it begins and where it ends, are fuzzy rather than sharp. The definition of where one galactic structure ends and another begins is somewhat arbitrary. The arm is a density enhancement, not a walled corridor. The transition between denser arm material and sparser inter-arm material is gradual. This is not a failure of measurement. It's a reflection of what the arm actually is. A statistical overdensity in a continuous distribution of stars and gas, not a physically distinct, sharply bounded object. The best current data puts us roughly midway through the arm's width and roughly between a third and halfway along its length from one end, but with real uncertainties attached to both of those estimates. What we know with confidence is that we're inside a substantial spiral feature of the Milky Way, that the arm extends for many thousands of light years in all directions from our solar system, that it contains billions of stars, dozens of active star-forming regions, and a wealth of structure that we've only begun to characterize in detail. The imprecision in the specific numbers doesn't undermine any of that. The arm is real. It's large. We're inside it. The exact boundaries are a question of definition, and the map is still being drawn. One more thing. The Orion Arm is silent. Not metaphorically silent. Physically silent in the deepest sense. There are no sound waves in the interstellar medium. Sound requires a medium dense enough to transmit pressure waves, and the interstellar gas is far too thin for that. The supernova that carved out the local bubble 14 million years ago released energy equivalent to roughly 10 to the power of 44 joules, a number essentially incomprehensible in everyday terms. And it happened in complete silence. The shockwave it sent into the surrounding gas was not a sound wave. It was a pressure wave in plasma. From any meaningful distance, there would have been nothing to hear. Just the sudden brightening of a star, and then its expansion into a glowing cloud. The births of new stars in the Orion Nebula, right now, are happening in silence. The churning of gas into protoplanetary disks around newly forming stars is happening in silence. Betelgeuse's eventual supernova, when it comes, will be the most dramatic event in the local galaxy on human timescales. It will happen in silence. The arm is full of the most extreme physical processes in the known universe: stellar explosions, plasma at millions of degrees, magnetic fields threading through hundreds of light years of space, shock waves from dying stars sweeping through molecular clouds. And all of it, every bit of it, plays out in a silence so complete that the concept of sound doesn't apply. We project the physics onto human scales. We imagine the roar of a supernova. We imagine the crackling energy of an ionized nebula. But none of that is real. The arm operates on its own terms, in its own medium, following its own physics, with no concession to whether it's perceivable by the sensory systems of small biological organisms on one of its planets. The only thing that crosses from the arm to us is light, and we have spent several centuries learning to read it. That exchange, light leaving the arm and minds inside the arm, interpreting it, is the only conversation between us and the structure we live in. It's an asymmetric conversation. The arm doesn't receive our questions, but it keeps sending the answers. And we keep learning to read them more clearly. Tonight, you've looked at the arm that contains you, not in the casual, abstract way that knowing you live in the Milky Way might provide. In detail, with some understanding of what it actually contains, how it's structured, where we sit inside it, what the processes operating within it are, and what the scale of it actually means. The Orion Arm is tens of thousands of light years long. It contains billions of stars. It's filled with molecular clouds assembling into new solar systems right now. It holds the local bubble, a cavity carved by ancient supernovae that shaped where nearby star-forming regions sit today. It contains candidate worlds for life, in numbers that dwarf the entirety of recorded human thought about the subject. It has been here for hundreds of millions of years and will be here for hundreds of millions more. And we are a small thing inside it, on a small planet, around an ordinary star. who have spent a few centuries building instruments and developing mathematics precise enough to see the structure we're embedded in and understand something about what it is. The scale makes us small. That's true. But the scale doesn't make us meaningless. Meaning is not something the universe distributes in proportion to size. What we've done, what we're doing right now, looking at the Orion Arm and comprehending even a fraction of its structure, is not made less significant by the fact that the arm doesn't know we're here. It's made more significant by the fact that we are looking despite being so small. That we figured out the arm exists at all. That we measured its length and width. That we traced the local bubble back to the ancient supernovae that created it. That we pointed telescopes at molecular clouds 1,000 light-years away and read the chemistry forming inside them. That we detected protoplanetary disks around newly forming stars and saw the beginnings of solar systems that might, billions of years from now, contain their own planets with their own histories. All of that from a small rocky world around an average star in a minor arm of an ordinary galaxy. The universe gave us a very small platform, and we used it to see almost everything. Good night.